Hello everyone, this is 18th lecture, and in this lecture we shall discuss about the electric field intensity due to uniformly charged spherical shell. The application of Gauss theorem, this is the third and last application of Gauss theorem, and for this we consider a spherical shell. A spherical shell is a hollow sphere with negligible thickness. So when we give a charge to the spherical shell, it is all distributed along its outer surface uniformly. Let the radius of the spherical shell is capital R and charge given to the shell is Q. Consider a spherical shell of radius R. Spherical shell means a hollow sphere with negligible thickness, just like inflated balloon. A spherical shell of radius R, a charge Q is given to it, which is uniformly distributed along its whole outer surface. Because this is hollow inside the shell, so no charge is distributed inside it, and all charge is uniformly distributed along its whole outer surface area. And then we consider three cases: the electric field intensity outside the shell, electric field intensity on the surface of the shell, and electric field intensity inside the shell. Now first we consider first case, electric field intensity outside the shell. If we consider a point A distance r from the center, then small r is greater than capital R. This is an electrical shell of radius r, and we consider a point. This is the center of the spherical shell, and this is the point P outside the shell at distance small r. And then in order to calculate the electric field intensity from Gauss theorem, we consider a spherical Gaussian surface of a radius small r that covers so this is the spherical Gaussian surface that covers the whole shell. Consider a point P at distance small r from center O then when we consider a Gaussian surface of radius r, then from Gauss theorem. According to Gauss theorem, surface integral of electric field intensity means net outward flux is equal to summation q upon epsilon naught. Here we consider a small area element, then electric field intensity E and surface area, direction of surface area dA are along same direction. So integral E dA cos 0 is equal to the charge enclosed by the Gaussian surface, that will be equal to the charge given to the spherical shell, means q upon epsilon naught. E can be taken out because we know that according to the characteristic of Gaussian surface, electric field intensity is same at all points. So it can be considered as a constant and taken out from the integral, and integral dA is equal to q upon epsilon naught. The value of dA will be the area of spherical Gaussian surface, and it will be 4 pi r square is equal to q upon epsilon naught, or E outside is equal to q upon 4 pi epsilon naught r square. We know that 1 upon 4 pi epsilon naught is equal to k. So E outside will be equal to kq upon r square. Means in this case, the spherical surface, spherical shell act as a pointed charge, or the charge given to the spherical shell behaves like a pointed charge. E outside is equal to kq upon r square. The second case, electric field intensity on the surface of the shell, This is the second case, and in this case again we consider a spherical shell of radius r, and q charge is given to the surface, which is uniformly distributed along its all open outer surface. And in this case we don't consider the Gaussian surface. This shell act as a self-Gaussian surface, and we can apply the Gauss theorem. Consider a shell of radius r. Hence, in this case, small r is equal to capital R, and point P is considered at this point on the surface of the shell. Consider a shell of radius r, and q charge is given to it. The shell itself acts as Gaussian surface. So from Gauss theorem, integral E E dot dA, the mathematical form of Gauss current, is equal to summation Q upon epsilon. Integral E dA cos 0 due to same reason, because the direction of electric field intensity will be this. The direction of considered area element is also same. So cos 0 is equal to the charge enclosed by the Gaussian surface Q upon epsilon naught, because whole charge is assumed to be concentrated at the center of the shell. So Q upon epsilon naught, E can be taken out according to the characteristic of Gaussian surface. E dA is equal to Q upon epsilon naught, and area of Gaussian surface will be equal to the area of spherical shell. 4 pi r square is equal to Q upon epsilon naught, and E is equal to 1 upon 4 pi epsilon naught Q upon r square, or KQ upon r square. This is the electric field intensity on the surface of the shell, and this is the maximum electric field intensity which is obtained on the surface of the shell. Outside the surface, since small r is greater than the capital R, so in this case the electric field intensity will be smaller than the electric field intensity on the surface of the shell. So this is the second case. Electric field intensity on outside the surface is KQ upon small r square, and electric field intensity on the surface of the shell, that will be KQ upon capital R square, and this is the maximum electric field intensity. Now we consider the third and last case in which we shall calculate the electric field intensity inside the shell. The third and last case, electric field intensity inside the shell. Means in this case, if we consider the point P inside the shell, means small r is less than capital R. And this is the spherical shell of radius r. Q charge is given to the shell. The radius is r, charge is q, and we consider a point P inside the shell at distance small r from P, from the center O. Then in this case, since the whole charge is distributed out at the outer surface of the shell, so no charge will exist inside the shell, and electric field intensity will also be equal to 0, because the charge enclosed by the Gaussian surface, which will be inside the shell, the magnitude of charge will be 0 enclosed by the surface, so electric field intensity will be 0. Consider a Gaussian surface, consider a spherical shell of a radius r, and Q charge is given to P is a point, P is a point at distance r from center O inside the shell. Consider a Gaussian surface of radius r is shown in figure. And then from Gauss theorem, integral E dot dA is equal to summation q upon epsilon naught and again E dA cos 0 is equal to the charge enclosed by the Gaussian surface is 0 because whole charge is distributed on the outer surface of the shell upon epsilon naught. So E is equal to E into 4 pi r square is equal to 0 or E is equal to 0. So inside the shell electric field intensity will be 0 because whole charge is distributed on the outer surface of the shell. So there are three cases. Outside the surface, electric field intensity outside the surface will be kq upon small r, and electric field intensity on the surface of the shell is kq upon capital R square. This is the maximum electric field intensity, and inside the shell is 0. If we draw a curve for that, so here we consider electric field intensity. This is R is equal to 0 at the center of the surface, and at the center of the surface electric field intensity will also be equal to 0. At the center it is also 0 inside the shell and center. So from the center to the surface the electric field intensity is 0 because charge is 0, and this is the maximum electric field intensity, means kq upon capital R square, maximum electric field intensity. From this point to this point, this is on the surface, small r is equal to capital R, and here since q is equal to 0 at the center, electric field intensity is also 0, and inside the shell electric field intensity will also be equal to 0. So q is equal to 0, then E is equal to 0, and then this is the maximum electric field intensity kq upon capital R square, and then when one goes from small r is greater than capital R, this is outside, this is on surface, and this is inside, and electric field intensity decreases just as, and the shape of the curve will be parabola, because E is inversely proportional to R square. So this is the whole about the electric field intensity due to uniformly charged spherical shell.